Welcome back, class. So now we're going to look at yet another example of a problem. And here we're going to be looking at a problem where the math becomes a little bit unwieldy. So in previous problems, we've had second order equations either that we could solve directly algebraically or we could solve using a quadratic equation. But what if we have higher order equations? Now, technically, this could be used instead of doing the quadratic, but solving a quadratic is not that hard, and you might as well solve it directly without doing any kind of approximation. But sometimes we get to things that we can't or don't want to solve directly because it's going to take lots of effort, and we're not going to be able to do it by hand anyway. And so there's certain approximations we can do to simplify the math. Now, there are some constraints on when these approximations can be used. So the big criteria we use is that when we have a small equilibrium constant, we know that the position of equilibrium will favor the reactant side. So that means there's not going to be a whole lot of product formation. So the reaction's not going to be moving to the right very much. So the change in product concentration is not going to be very much, and that means, the change in reactant concentration is not going to be very much either. Now, if we couple these small changes with a relatively large initial concentration, then the actual percentage change, if you will be, insignificant, right? So if we have a large value and we have a small change, then the final value, our equilibrium value, isn't going to be very different than our initial value. And so essentially what we're doing here is we're assuming that, or making the assumption that, at least based on, magnitude of change where we know it, right, that we have an insignificant change in these concentrations. So we can say that our reactant concentration, if starts out large, we have a small constant change because we have a very small equilibrium constant, that we can assume that change is essentially zero. Now what that means is that our equilibrium concentration is going to be approximately equal to our initial. So we're basically saying that this value of AX here is insignificant. Okay, so let's see how that might play out. But remember, we can make this assumption if we have small k's, large initial concentrations. Now, typically we're talking reactant concentrations, but if we were moving the other way, I guess we could be talking about product concentrations. But the initial concentrations that we know are going to be large. Now, just like with any approximation, we'd like to check to make sure it's going to be good approximation. So once we solve through the problem using our approximation, because that'll simplify the math, then we can go back and check to see if that approximation is valid, whether it's, whether we introduce too much error by making that approximation, and sort of the cutoff or where we find it acceptable to make that approximation is if the approximate value that we calculate for X is less than 5% of the initial concentration. So another way of saying that is if the change in our initial concentration is less than 5%, then we can say the approximation is valid. Now the way that we would calculate that would simply to take our approximate value of X we get when we use the approximation, divided by the initial concentration times 100 to see if we have less than a 5% change. Okay, so that's how we're going to approach that. So let's introduce our first problem here, or at least the problem that we're going to use to show this example. So we have the equation of 2H2S is in equilibrium with 2H2 plus 1S2. and we're given a k of 1.67 times 10 to the minus 7. So we can initially see that this is a small value, right? This is a very reactant-favored equilibrium, and so we don't expect much product change or much product formation based on this equilibrium constant. So if we have starting concentrations of 0.025 for our reactant and no product, so we go through our sort of thought process, and the first thing, since we don't know anything about the equilibrium, the first thing is we have to establish which direction the reaction is going to move to get toward equilibrium. Now, this is again one of our extremes where we have no product, so Q equals 0, so we know it has to move to the right, meaning we're going to increase the products, and our reactant here is going to go down. So let's define our changes in terms of our variable. So we have a 2 to 2 to 1 stoichiometry. So there's multiple ways that you could do this, but to keep it simple, I'm going to just use our coefficients here, and I'm going to define my change in H2S as minus 2x. And I'm going to define my increase in H2 as positive 2x. And I'm going to define my increase in S2 as just x. So of course, you could also define this as minus x plus a half an x. You know, that's fine. But this, I think, keeps it a little more straightforward. We don't have those 0.5 values here. So let's write out equilibrium concentration expressions using this change. So we end up with 0.0250 minus 2x. We have 0 plus 2x, or simply 2x. And we have 0 plus x, or simply x, as our equilibrium concentration of S2. So now we have our expressions that we could then write out. So we're gonna next work through solving this equation. Okay, so let's solve this problem based on what we just found in our ICE table. So here's our equation, our chemical equation. We have our K value. And so let's first write out our generic K expression. So we're going to have products. So we're going to have our concentration of H2 squared times our concentration of S2 raised to the first power over the concentration of H2S squared. So now we can plug in the numbers that we know. So we know K is 1.67 times 10 to the negative 7 equals, from our ICE table, we found H2 had an equilibrium concentration of 2x squared. S2 had a value of x. And H2S was 0.0250 minus 2x squared. So we have our equilibrium expression, and our goal now is, of course, to solve for x. Now, if you're used to doing some algebra here, you realize that we're going to end up with a higher order equation here, a cubic, if you will. So let's just simplify some of this. So we can work on the right side here, and on the top we have 2x squared plus x, or times x. So the 2x squared, we get 4x squared times x. We're going to get 4x cubed on the top. Over 0.0250 minus 2x squared. So when we get to this point, this is where we start to think, okay, this is not going to be something I can solve directly. It's not going to be something that I can solve using a quadratic. I'm going to have to use a higher order expression to solve this if I leave it this way. So this is where the approximation comes in. And remember, that approximation is taking changes in terms of x and setting them equal to 0. So if we take our reactants down here, and we had a change of minus 2x. So since we have a small k, and we'll see if this is reasonably large enough, but probably is, but we'll check that at the end, of course. We're going to take this change and we're going to assume it is 0. So what that means is we're going to make our approximation, and our rewritten equation now is 4x cubed over 0.0250 squared. Okay, so this is a lot more straightforward. So now we just have x in one place, and we're not going to end up with cubic terms and squared terms and x terms, etc. So now let's rewrite our k value here. Now it's a matter of sort of just solving the algebra. And I'm not going to go through all the algebra here, but if we rewrite this as 4x cubed over 0.0250 squared, which is 6.25 times 10 to the negative 4. So now we can take our numeric value, we can bring it over to the left side of the equation. So we can do some simplification. I'm just going to do partial simplification here. So let's do 1.67 times 10 to the minus 7 times 6.25 times 10 to the minus 4, all divided by 4, equals x cubed. Okay. So I brought the 6.25 times 10 to the negative 4 over to the left side. I divided both sides by 4, bring that over to the left side. So we're isolating x here on the right side. Now we can get a value for the left side of the equation. So we simplify this, we're going to get 2.609 times 10 to the minus 11 equals x cubed. Now we have to take the cubic root of that, and I'm going to move up here. So if we take the cubic root of this, we get 2.97 times 10 to the minus 4 equals x. So now we've solved for x. Okay. All right, so that seems perfectly fine. But before we go about actually solving for our concentrations, let's see if this approximation is valid here. So remember, the way we do that is we take our approximated value of x using this approximation. So that's 2.97 times 10 to the minus 4, divided by our initial concentration, which was 0.0250, and times that by 100 to put it in terms of a percentage. And what we end up is 1.19%, right, which is clearly less than 5%, which is our benchmark. So what we can say here is the approximation is valid here. We aren't introducing a whole lot of error. We can go ahead and use this to calculate our equilibrium concentrations. So at that point, we're going to plug back in. So the concentration of H2S is 0.0250 minus 2 times 2.97 times 10 to the minus 4. So we go all through that, we end up with 0.0244 molar. Now we go for H2. So H2 was simply 2 times X. So 2 times 2.97 times 10 to the minus 4, which equals 5.94 times 10 to the minus 4 molar. S2 is just simply equal to X, and so of course that's going to be 2.97 times 10 to the minus 4 molar. So at this point we've solved for our concentrations. Now, one thing we don't want to forget, so these problems can sometimes get a little bit lengthy, is we've gone through all this algebra. We want to make sure that we did it all correctly. And so we're going to plug these values back into our original K expression to see if we get a similar value of K to what we were provided with. So K equals 5.94 times 10 to the minus 4 squared times 2.9 7 times 10 to the minus 4 divided by H2S squared, or 0.0244 squared. So if we do all that, we should get a K that equals 1.76 times 10 to the minus 7, which we can see is the same K, or basically within reason the same K that we were provided. So we were given 1.67, this gives us 1.76, so the approximation isn't instituting much of an error. And so you got to remember, any difference that we're seeing here is out in the 8th decimal place, right? Or way out. So this is a tiny discrepancy. So that's an example of a problem where we can use this approximation as a way to work through.